Så er vi klar her. Værsgo.
Kan I se mig? Og høre mig?
Der er kun gråt billede på.
Kan du se og høre mig?
Vi har kun gråt billede her. Du lavede noget med kameraet før.
Jamen, velkommen. Welcome to this double degree PhD defense by Føroya.
Lars, vi har ikke noget billede fra dig. Der er bare sådan et gråt billede. Har du muted kameraet? Der var du. Tak.
Now you can also see me. Welcome to this double degree PhD defense. My name is Lars Nybo, and I'm presenting both the University of Copenhagen Faculty of Science and also the University of the Faroe Islands, where Toro has completed his very impressive large work that I'm looking forward to both hearing Toro's presentation here within the next approximately half an hour. After that, the first opponent, Hanne Rasmussen, will examine Toro. There will then be a very brief break before our second opponent, Truls Rastad from Norway, will take over and complete the examination. After that, there will also be the possibility for you from the audience to ask questions to Toro. And after that, the committee will meet and evaluate the defense, and we will then invite all of you back to the conclusion. But with these words, I hand over the presentation to Toro.
Thank you. Thank you, Lars. I would like to begin by welcoming the assessment committee, my supervisors and my colleagues, and also a very warm welcome to friends and family. I really appreciate seeing so many familiar faces. The title of my PhD thesis is The Importance of Angiotensin-Converting Enzyme Activity for Adaptation to Exercise Training. I would like to start my presentation by providing you with an overview of the conducted studies and associated papers during my 3 years of doctoral study. My dissertation is based on work from 2 comprehensive randomized controlled trials, from which 4 original papers have been produced, 3 of which have been published. In study 1, healthy participants were randomized to exercise combined with ACE inhibitor treatment, or placebo. And in paper 1, we assessed the impact of ACE inhibition on cardiovascular adaptations to exercise training. And in paper 2, we assessed the impact of ACE inhibition on the local muscular adaptations to exercise training. In study 2, patients with coronary artery disease were randomized to either exercise or standard care. And in paper 3, we assessed the impact of exercise training on VO2 max improvements. And in paper 4, we assessed whether the VO2 max improvements seen in paper 3 were dependent on the patient's ACE genotype. Here I have outlined the agenda for today very simplistically. First, I will introduce you to the topic. Then I will talk about study 1 and the 2 papers pertaining to study 1. This will be followed by a brief review of study 2 and the associated papers 3 and 4. And finally, future directions and practical learnings will be reflected upon. We're different as physiological human beings, and personalized exercise is a relatively new area of research aiming at individualizing exercise to personal traits. The idea here was to use a well-known pharmacological compound to identify a potential source of variability in human training responsiveness. In relation to public health, any determinant of exercise trainability is of relevance, because the ability to adapt to exercise training is of paramount importance for health. For instance, if we look at exercise capacity as measured by VO2 max, it is highly responsive to exercise training and is widely considered the best reflection of whole body health and function. This figure by Emboden and colleagues shows that VO2 max levels are inversely related to mortality risk in healthy individuals. They also showed that for each 1 MET increase in VO2 max was associated with a 12%, 16%, and 14% reduction in all-cause cardiovascular disease and cancer mortality. And this is independent of traditional risk factors. But what is VO2 max? VO2 max is a complex phenotype bounded by two components of the Fick equation: the cardiac output, which is the stroke volume and heart rate, and arteriovenous oxygen difference. And endurance training is linked to numerous physiological modifications that may influence VO2 max. And these are typically categorized into two broad phenotypic modifications that enhance either oxygen delivery or oxygen extraction. And enhanced oxygen delivery is mainly caused by increases in the oxygen carrying capacity of the blood volume, increases in left ventricular dimension and compliance. And enhanced oxygen extraction is mainly caused by increases in skeletal muscle capillarization and increases in mitochondrial density and oxidative capacity. And these physiological modifications highlighted here are the underlying adaptations that are largely driving the health beneficial effects of VO2 max improvements. And in this figure, they're all pointing towards VO2 max or the Fick equation, but it should be emphasized that there's an independent potential health effect of an increased capillarization, of an increased oxidative capacity, of an increased blood volume, and so forth. And a training intervention can, for instance, improve the participants' physiological capacity without improving their VO2 max. And these effects are then only revealed if you include a broad spectrum physiological assessment, what we call a deep phenotyping in my study. It is largely accepted that all humans can adapt to exercise training, given that the training stimuli is sufficient. However, it is beyond dispute that humans vary in their ability to exercise training. This is perhaps best illustrated in the Heritage Family Study, in which more than 700 healthy sedentary individuals completed 20 weeks of endurance-based training. The authors reported a mean gain of 400 milliliter in VO2 max, but the changes ranged from a reduction in VO2 max to an increase of more than 1,000 milliliter. And this heterogeneity in training responsiveness is one of the most crucial issues in exercise medicine. And understanding which factors contribute to the variability in training responsiveness is fundamental. When looking at potential predictors of the VO2 max response level in the Heritage Family Study, Sarsinski and colleagues found that baseline VO2 max, age, gender, weight, ethnicity only explained between 2 and 3% each. However, they found that heritability explained almost 50% of the variance in VO2 max response levels. And this indicates that genetic factors contribute substantially to VO2 max trainability. But the question is, which genes or genetic factors are responsible for this variation? From 2000 to 2008, Bray and colleagues published an annual review of all genetic markers associated with exercise trainability. This is an overview of chromosomes and potential genetic determinants for the human exercise training responsiveness. Currently, however, none of the identified candidate genes to date have been validated as true causal genes for exercise trainability. And it is widely recognized that for progression to occur in the exercise genomic research field, there's a need for a higher engagement in intensive mechanistic research on phenotypical traits from one or a few of these genetic candidates. On chromosome 17 is the gene that encodes the angiotensin-converting ACE enzyme, abbreviated ACE. Today, the ACE gene is by far the most studied gene for human variation and exercise trainability. The ACE gene contains an insertion-deletion polymorphism that accounts for almost 50% of the total phenotypic variance in serum ACE levels. This indicates a clear genotype-phenotype interaction in which carriers of the II genotype have low serum ACE and carriers of the DD genotype have high serum ACE. The interesting part here is that the physiological phenotype based on the ACE genotype may influence exercise trainability. The first indications came from the seminal papers from Montgomery and colleagues in the late 1990s. In 1997, they investigated changes in left ventricular mass in response to 10 weeks of endurance-based training. This was done in 140 healthy military recruits. They found that the training intervention induced a 40-gram larger increase in left ventricular mass in carriers of the DD genotype compared to carriers of the II genotype. 1 year later, the same research group investigated changes in muscle endurance in response to 10 weeks of endurance-based training, and this time in 80 healthy military recruits. The training intervention induced an 11 times greater increase in muscle endurance in carriers of the II genotype compared to carriers of the DD genotype. Since these studies, hundreds of studies have investigated the interaction between the ACE genotype and the ability to adapt to exercise training. The literature points in different directions, which should be expected as these are complex sports phenotypes that are being investigated. However, an association between the ACE-II genotype and enhanced endurance performance has been confirmed by a meta-analytic approach. And in this review article from Putukiari and colleagues, the authors concluded that the ACE-ILL is indeed associated with endurance-oriented performance, and the ACE-DLL is associated with strength and power-oriented performance. In this context, it should be emphasized that the vast majority of the included studies are cross-sectional studies. So, we know that the ACE genotype is a strong determinant of serum ACE levels. So there's a genotype-phenotype interaction. We also know that the ACE genotype may impact performance phenotypes and exercise trainability in humans. But what we don't know is whether the underlying cause for the ACE genotype to interact with the response to training is related to ACE genotype-dependent differences in serum ACE levels. And so to investigate that, we can manipulate the ACE phenotype pharmacologically with ACE inhibitors. So, combining ACE inhibitor treatment with exercise training can be used to determine if serum ACE activity is a determinant for exercise trainability. ACE inhibitors are well-known, worldwide used antihypertensive drugs that inhibit the ACE activity. And therefore, they actually mimic the phenotype characterized by the II genotype. And this has led to the idea of a possible additive effect of ACE inhibition on endurance performance. However, the few human studies assessing the impact of pharmacological ACE inhibition on the adaptation to exercise training have yielded conflicting results. Beaufort and colleagues found a synergistic effect of combining exercise training with ACE inhibitor treatment on 400-meter walking speed, whereas Baptista and Sumukatas found no effect. There are some issues with these studies, however. Firstly, they exclusively recruited patient populations. And we know that comorbidities and the concomitant use of various medical treatments makes it incredibly difficult to interpret the results. In addition, they have not controlled for types and dosages of ACE inhibitors, and they have focused on discrete outcomes such as 6-minute walking distance, which is a simple applied test with obvious translational value into everyday life, but it doesn't really increase our basic understanding of the physiological adaptation to exercise training. Therefore, the main objective in Study 1 was to assess the impact of pharmacological ACE inhibition on broad-spectrum physiological adaptations in response to high-intensity interval training in a healthy homogeneous population without confounding diseases and treatments. Specifically, the inclusion criteria were that the participants were aged between 20 and 50 years old, no cardiovascular disease, and not treated with any medications. In addition, an inclusion criteria was that they were untrained, which in our study equals not systematically trained. 52 participants, 26 females and 26 males, were enrolled in the study. And 48 participants, 24 females and 24 males, completed the study. A randomized, double-blind, placebo-controlled design was applied. Following a screening, participants were randomized to ingest either placebo or the ACE inhibitor enalapril for 8 weeks combined with exercise training. The maintenance dosage was 20 milligrams per day. The randomization was stratified by gender and ACE genotype, and the pharmacological compounds could not be distinguished by taste or appearance. A comprehensive physiological assessment, a so-called deep phenotyping, was performed pre- and post-intervention. The age, height, weight, and body mass index were similar between groups. Exercise training was completed as high-intensity interval training on a rowing ergometer. 3 sessions a week for 8 weeks. The effective training time was 25 minutes per session, corresponding to around 75 minutes of effective training per week. High-intensity interval training was used based on substantial scientific evidence on its effectiveness for inducing broad-spectrum physiological remodeling, including increases in VO2 max and muscle oxidative capacity, also when compared to moderate intensity exercise training. And what about rowing? We tend to think dichotomously endurance or resistance type training. But an example of a combined endurance and strength type training stimuli is rowing. There's repetitive contraction of large muscle groups, and every time you pull on the handle, there's a huge increase in arterial pressure from a combination of large muscle mass contractions and a huge increase in stroke volume. In addition, all sessions were supervised, power output was continuously monitored and logged, and we had an incredibly high adherence of 99.9% to the exercise sessions. The average relative power output of more than 110% confirms that the training was high intense. The average, and importantly, the average power output and relative power output was similar between groups. And now I'll go through the comprehensive physiological assessments. VO2 max was assessed by a maximal incremental exercise test on a cycling ergometer. Whole body work capacity was assessed by a 6-minute all-out effort on a rowing ergometer. And upper body muscle endurance was assessed by a custom-made muscle endurance test to exhaustion. Cardiovascular magnetic resonance was used to assess changes in left ventricular volume and mass. Echocardiography was used to assess changes in left ventricular diastolic function. And the carbon monoxide rebreathing method was used to assess changes in the oxygen carrying capacity of the blood and in the blood volume. Muscle biopsies were obtained both from the deltoideus and the muscle vastus lateralis, because studies have shown that both muscle groups are active during the rowing movement, and because previous studies have shown that the adaptation to exercise training is muscle group specific. Obtained muscle biopsies were used to analyze changes in markers of mitochondrial volume density, oxidative capacity, and angiogenesis. DEXA scan was used to assess changes in body composition, and a hand grip dynamometer was used to assess changes in maximal hand grip strength. Now I'll go through the results in Study 1. Please note that the sample size in Study 1 was determined to detect between group differences of 20% in the primary outcomes, and the primary outcomes were VO2 max and muscle endurance. All subsequent analysis are of course a result of this power calculation. To evaluate the efficiency of the pharmacological intervention, we assessed changes in blood pressure and serum ACE activity. This figure shows blood pressure measured at home, morning and evening, the initial 2 weeks of the intervention. And what we can see is that ACE inhibitor treatment reduced mean arterial pressure from day 2 and onwards. And the between-group difference existed from day 9 and onwards. We also measured mean arterial pressure at the hospital pre- and post-intervention, and what we found was that ACE inhibitor treatment caused a 6% reduction in mean arterial pressure, while no changes were observed in the placebo group. And for serum ACE activity, we found a 32% reduction following ACE inhibitor treatment, and a borderline significant 20% reduction in the placebo group. Exercise training increased all measures of exercise capacity significantly, but there was no effect of the treatment. VO2 max increased by 13% in both groups, muscle endurance increased by 70% in both groups, and rowing performance by more than 30% in both groups. With regards to the hematological adaptations, we found a between-group effect for all of the obtained measures. Blood volume increased by 3% in the placebo group, whereas a numeric 2% decrease was observed in the ACE inhibitor group. Plasma volume increased by 4% in the placebo group, whereas a numeric 1% reduction was observed in the ACE inhibitor group. With regards to red blood cell volume and hemoglobin mass, we observed a significant 3% reduction in the ACE inhibitor group and a numeric 2% increase in the placebo group. And these findings may have clear end-diastolic volume, stroke volume, ejection fraction, or mass. However, a borderline significant between-group effect existed for left ventricular end-diastolic volume, which moved in opposite direction in the two intervention groups. In accordance with the lack of cardiac remodeling in our study, Arbab Shadeh and colleagues have reported that 3 months of endurance training are required to see changes in left ventricular mass and stroke volume, and 6 months of training to see changes in end-diastolic volume in previously sedentary individuals. However, a significant between-group effect existed for echocardiography-determined left atrium volume, which increased by 14% in the placebo group and by 9% in the ACE inhibitor group. But no consistent pattern of improvement was observed in diastolic function in either the ACE inhibitor or the placebo group. We assessed the impact of ACE inhibitor treatment on the local muscular adaptations to exercise training. As I noted previously, the study was designed to have sufficient power for detecting differences in VO2 max and muscle endurance. The muscle analysis tend to have a higher variability compared to, for instance, VO2 max. In other words, we know that power is inversely related to variance of a particular outcome. So in other words, we have a higher risk of committing type 2 errors in the muscular analysis. And so the results should, of course, be interpreted with caution. Citrate synthase and HAD maximal activities can be used as biochemical markers of mitochondrial oxidative capacity and density. In vastus lateralis, citrate synthase increased significantly in both groups, but with no difference between groups. HAD maximal activity also increased significantly in both groups, but with no difference between groups. In the deltoid, however, citrate synthase increased by 52% in the placebo group, which was significantly higher than the 27% increase in the ACE inhibitor group. In addition, HAD maximal activity only increased in the placebo group. But again, with low power, we are only able to detect big effects while we're missing medium and small effects most of the time. So if we look at the highlighted figure here, the non-significant 16% increase in the ACE inhibitor group could possibly be a type 2 error. And also the non-significant interaction effect could also be a type 2 error. Platelet endothelial cell adhesion molecule 1 was used as marker of skeletal muscle angiogenesis. In vastus lateralis, PCAM protein abundance increased significantly in both groups, but with no differences between groups. In the deltoid, only the ACE inhibitor group demonstrated significant improvements in PCAM1 protein abundance. But again, given the extremely high variation and low sample size in the placebo group, the non-significant within-group effect may be a possible type 2 error. Our key findings in papers 1 and 2 are that exercise training induced improvements in maximal oxygen uptake, whole body work capacity, muscle endurance, muscle oxidative potential, at least in the lower body musculature, and skeletal muscle angiogenesis are independent of ACE inhibitor treatment. However, ACE inhibitor treatment caused a reduction in left atrium volume and a reduction in the oxygen carrying capacity of the blood. In addition, ACE inhibitor treatment counteracted the training-induced increase in lean body mass. Now I will go to study 2. Study 2, which was the exercise training study in patients with coronary artery disease. It was initiated by the medical doctor and fellow PhD student Jakobina Christiansen. And we saw this as a fantastic opportunity to engage in a training study with a clinical population and to collaborate across disciplines. So study 2 represents a joint effort between exercise physiologists, cardiologists, medical doctors, with my primary tasks being related to the training intervention and the VO2 max measurements. Interestingly, studies have shown that the ACE genotype may impact VO2 max trainability in patients with coronary artery disease. This was shown by DeFore and colleagues, who investigated VO2 max response levels were ACE genotype dependent in elderly patients with coronary artery disease. They found that carriers of the II genotype had the highest VO2 max improvements following 12 weeks of exercise training. The main objectives in study 2 were to investigate the impact of low volume, whole body, high intensity interval training on VO2 max improvements in elderly patients with coronary artery disease. And so paper 3 is not directly related to the main theme of the present thesis, but we used the data from paper 3 to establish whether improvements in VO2 max were ACE genotype dependent in this patient population. And that is, of course, of high interest to this particular thesis. We hypothesized that carriers of the II genotype demonstrate greater training-induced improvements in VO2 max compared to carriers of the DD genotype. 169 patients were enrolled in the study, and 142 patients completed the study. Patients were randomized to 12 weeks of high-intensity interval training or standard care. VO2 max was determined pre- and post-intervention by means of a maximal incremental exercise test to exhaustion. As you can see, the patients were elderly individuals, predominantly males, but no differences existed between the exercise and the standard care group. Exercise training was completed as high-intensity interval training on a rowing ergometer. 3 sessions a week for 12 weeks, 18 minutes effective training time per session, corresponding to approximately 54 minutes of effective training time per week. High-intensity interval training was applied in this study as meta-analysis data has shown that high-intensity interval training appears to be superior to moderate-intensity continuous training for improving VO2 max. All sessions were supervised. Again, we had an incredibly high adherence to exercise session of 97%. Power output was monitored on weeks 3, 6, and 9. The average relative power output of 117% confirmed. What we found was that exercise training of a training study in terms of comparing a training group. So now we had 2 groups, carriers of the ILL compared to carriers of the DD genotype. And again, what we found was that exercise training significantly improved VO2 max in both genotype groups, but with no difference between groups. So the conclusion in study 2 was that combining low volume, high intensity interval training and standard medical treatment efficiently improves VO2 max with no effect of the ACE genotype in elderly patients with coronary artery disease. The hypothesis that carriers of the II genotype demonstrate greater training-induced improvement in VO2 max compared to carriers of the DD genotype was rejected. Take-home messages from both studies. Exercise training aimed at augmenting VO2 max and skeletal muscle oxidative capacity appears to be efficient with and without ACE inhibitor treatment. However, of the blood, patients with coronary artery disease, of course, is required in order to extract, and future studies should the outcome of exercise training. ACE inhibitor treatment on cardiac randomized controlled trials with intervention, which is assessments. These operations and easy access during my doctoral study.
Så fint. Okay, thank you very much for choosing me as an opponent for this thesis. Maybe you were not so impressed by the first rejection and you thought that was a wrong choice. But I think that it really improved by a good method session. So I'm really thrilled for the discussion we are going to have. And at first I thought, wow, not many Danish cardiologists believe in the importance of exercise training, but here on the Faroe Island, they have realized the importance. And even though you are not going to become a cardiologist, I still want to congratulate you with having managed not only 1, but 2 randomized studies with exercise training. That is really impressive, and also including a lot of difficult methods. To well prepared, and for the well prepared, every examination. I think also it's not knowing how to perform HIIT training. As you all know, exercise of coronary artery disease, as well as oncology, after 12 weeks of in exercise capacity, better quality of life. And also shown that in real life, exercise-based cardiac rehabilitation and of the patients, 50% achieve an increase in and as you said, can be that patients does not gain any, and Bouchard and co-workers have shown cannot feel any improvement. The exercise program with paper 3 and 4. Then
here you are. Yeah. Whole events in their database. So that we could just look in the. However, there was a problem on day that didn't cover
the inclusion criteria. I couldn't find it. Okay. To either ACE, so you know, it was 100. So you go more than.
I believe that one of the reasons 15 physiological. That will be one of the and.
But once you got them, then
we had one dropout due to intertraining, of course.
Then comes the first. You said, the day's activity and concentration increase in LV mass by increased ACE.
The problem here is that it's difficult to find it's difficult to find the mechanism that explains what we're seeing in the literature, and what studies have shown, I think, is a growth factor that stimulates hypertrophy in myocytes, and they showed that, and that is and you have a higher production of angiotensin II.
Kind of hypertrophy are we talking about? Because now it comes a little bit cardiologist like, you have the normal geometry and then you have the remodeling. Either it's getting
based on what they and that was also my point with. We tend to think that some of the studies, the biggest hearts of any athlete, and concentric hypertrophy.
What would the D type, would that be the one?
Studies shown that elite swimmers or representation of the DLL.
You're trying to diminish, and then you choose, first of all,
between the intervals they were not standing.
I think they must have been like,
Yeah, they were like, and there were vomit bags with motivational quotes because there were some participants that,
so you had to reduce some of them?
We reduced to 10 milligrams for, I think, 4 or 5 participants.
Yeah. Okay. Then why did you choose an ACE inhibitor and not an AT2?
Yeah. If there's one, then it is that that the ACE ILL that they might have a higher nitric oxide bioavailability, and so if we go further downstream, then we won't hit the bradykinin pathway. So that's why we
choose that
ACE inhibitor.
Being a clinic down in terms of trainability.
That was also to increase. We don't know oxide bioavailability, of muscle contraction. We believed could have an effect, but we didn't see any effect on muscle endurance.
No. But that was a theoretic. Those on the AT2 antagonist. Okay. Just to confuse everybody by all these ups and downs here, but to say that, when you do use an ACE inhibitor, this is what you want to have, less vasoconstriction and hardly at all, but this might be a little bit of the explanation of the effect on the plasma volume, because otherwise, how do you explain that?
So it's the aldo that the plasma
part is the volume increase either, but everybody says that, and it's no
explanation.
We just put it there. Then you used a very high dose of ACE inhibitor, and by that you showed very fine, that the blood pressure went down, and at the same time you saw that, as would be expected, or whether you are DD, ID, or II, doesn't really change the response of the blood pressure. Impact on the blood pressure. I mean, the whole homeostasis is just, covered by having the right blood pressure. So, if you, maybe this is the next, then you go to the next, and I know that is a bit unfair to show that, because that, I guess, is really annoying for you, because here we would expect that the serum ACE here would be related to the different genotype, and it's not. not like we would expect it to, and why?
Yeah, but
That's just what happens.
It's a concentration.
Yeah. Okay. So could it be also when you see the reduction is related to dilution as well after exercise?
Yeah, what do you mean by dilution?
I mean, if you get an increased blood volume, then the concentration will decrease.
Yeah.
Because you have when you change the blood pressure as much as this, it's not also investigating a lot of other to A's and ARB, depending on a certain this, and quite difficult. And here you use two main focus, I guess, you have had here would be LV mass, because that was the main
cardiac MRI.
Yeah, that's the most absolutely
opposite direction, which
that in one group here you they are different. The mass. If you have the mass, so here they are having normal geometry. Yes.
Is that we want dilated hearts, we want an increased lymph course.
So a bit thicker and a bit bigger.
Yeah.
But then at the same time going there, and then you have the ACE inhibitor effect. So what would that do to the heart?
You don't work against the same pressure.
Precisely. Yeah. Have you tried that they were actually having different? They were different in.
No, we haven't looked at that. What I would say is that we have a problem there, because and in the DD genotype there's a clear overrepresentation of males. When we were trying to recruit participants, of course we wanted equal amount of every in ACE genotype, but we simply couldn't find it.
Just too difficult. And then follow up after 12 weeks of exercise, and whether they were in the placebo or the losartan. And they found that, by using losartan, they found that there was an effect of D were bigger beforehand, and they increased more. But the dose they were using losartan was quite low. I mean, that didn't have any influence on their blood.
Exists in Alapril.
You can, but
Okay.
You can. So, but that might be some of very try to separate them, and it's not completely fair, because endurance. If you look into elite athletes, like first having normal geometry, but what we see the most is the eccentric, dividing them into static, dynamic, or mixed exercise. And if we go into hypertrophy, actually, so we would expect the big heart here.
Well, some of them are active, are training.
Then at least 10 hours per week, or 15 hours. And if you could, although it was heavy work they were doing, and they did it 3 times a week, but and then comes the time as well, as you said, MR, and here you have the it's very high. MR result here from 3 months, and then you see that there's a change. So maybe that, like you said, going 2 different ways, and therefore difficult to see any effect on the heart. And that's going to then, is it the ACE inhibitor, or is it the exercise? It's just a little part. So it will be the drug.
Yeah, exactly.
Do we agree?
Yeah.
Or do you agree?
Yeah, I agree, yeah.
You did only examine the heart at rest.
Yeah.
And not during exercise, because that was
practical reasons.
I know, I understand. Yeah, but that's always what we,
resting values when we so we used mainly Starling curves and pressure volume curves, not methods I'm really familiar with, but I see a clear increases in the Starling mechanism, or in the Starling curve. So very
That's fine. That's completely what we would expect. So, about, training intensity, volume, sporting discipline, then there are also some kind of familiar.
I believe that if you train with the right intensity and the right volume, then anyone can.
Hard to adapt, or is it bad? In relation to exercise?
It's good.
It's not the genotype we look for, but we look for the BSA, the body surface area. I'm sure his heart is much bigger than mine. So you always have to correct for that.
Yeah.
And therefore, it's not a problem when they are there like you do here in the left atrium volume. Are they the same size? No, they're not at the beginning. So that would be, and therefore, how much do they change? 4 milliliter. The difference between the same measurements. Yeah. So saying this is a significant change. Did you just have one examiner, or did you small difference?
Yeah. Yeah.
And they are not completely the same from. So, could you have used other left atrium is very important for is of importance because the left. I'm getting a little bit. I'm a cardiologist, but measurement telling you something. You should always say, does it seem like? No, it doesn't.
Yeah, I saw some when animation.
Yeah, precisely. We talk about the left atrium actually works, and that would be informative, especially the other group. So that's just how that looks if you go into that. And cardiologists, because you see that athletes that are in accordance with the dilation, they also have left atrium gives you a high, and I now say that it might not really be relevant what you're saying here, even the first incidence of atrial fibrillation. Then we go to paper 3. And then you have 169 patients, and it's actually quite impressive that you made it. Same reasons why, like you said beforehand, for the healthy parts.
Yeah, 12 weeks of training that's intensive as in study 1, for instance.
To do this exercise anyhow. Yeah. But of course it's not.
Not a significant difference between the dropout in the 2 groups.
Or before start?
Yes.
Okay. Did you? No, you didn't.
We taught the randomization.
Then they were allocated, and then the main out.
Well, we could have also used new. Then you have to use a protocol that you are sure that, or you have to do an effort to make sure that this is the maximal oxygen uptake under any circumstances during the given test.
I would have done completely.
Yep, because they have some get up
the leveling off.
Leveling off.
Precisely. That was that.
Well, we had to be a leveling off. Sometimes we don't get the level.
Use other parameters. Do you use RER, 1 point rate, to ensure that you are what is expected? You say could be a problem in a patient with.
No, if they get overruled by.
Yes, precisely, and I've forgotten the other one. So I used to say, how do you say what is max heart rate? They wouldn't know, and if you, beta blocker is okay. It's something completely different. Yes, it is. So what was your variation of repeat?
Did that in percent, I think.
Is that good?
Yeah, it's good.
Quite good. Very good. But, and then, this is a little bit funny because training study, and then they said there's a sample size was calculated based on markers of fibrinolysis, and I thought, okay, now there's something that I do not understand.
Yeah.
Can you explain?
Yes. This was all of that, but laboratory restrictions, travel restrictions with coronary artery disease. And that was in restrictions. And
so that's also why you did not stratify, of course. Okay. Then here you got a. So why did you choose?
Yeah, and that's to discern.
Just to make it hard for yourself?
Yeah. That's to discern the physiological effect from the learning effect. There are several studies. There's a study in McArdle, the exercise physiologist, where there are untrained participants. They are going to a swimming intervention, and they test VO2 max on a treadmill, and during swimming, the VO2 max during swimming increased by 15 to 20%. We wanted to ensure that the adaptations that we saw, they were physiological adaptations and not related to an improved. These are not trained rowers. They've never sat on a rowing machine before, sensation with the rowing ergometer.
So that might be also explains that the increase was a bit
markedly higher.
Yeah, I'm sure. So what was it I was going to say about this? That you saw the oxygen increase, the standard care. That is probably what you see here, or how do you explain that?
Yeah,
monitor intensity, because if we are talking about, that's really the problem, I guess, especially about HIIT training. What I find, and maybe the reason why I'm saying so, is because of the very depressing on heart failure patients, and that came from the idea from Norway, where they, in the small size of investigations, found that it could actually a multi-center study. And what they found was that, they didn't increase diastolic diameter. But what was really the case is that if you don't take the medicine, it doesn't work, funny enough. So they found no difference was found between training records showed that, 50% of patients exercised below the described target during supervised HIIT and 90% above target because they were only doing 60 to 70%. So that's just saying that it is really difficult. How did you monitor? You actually said it. You did monitor it, didn't you?
Yeah, we did monitor, and we monitored power output on week 3, 6, and 9, and that was primarily just to see what was the relative power output compared to a 6-minute all-out test conducted. But what we did was that for each session, rowing experts supervising, so the evaluation of the intensity was that the supervisors.
It's a beautiful setup, but that is in clinical practice or in multi-center studies really difficult.
Yeah.
Not standard care, I hope, because what you meant by standard care, I guess, was nothing. I mean, they were not doing any exercise at all.
No. Just
to make it easy to say.
Yeah.
You get very practical when you've been a cardiologist. Ways do studies for a short period of time, and you can get excellent effects. But what really counts on the long way is whether they continue to do so. Every kind of theoretical, ideas about as we get older, we need to do some strength exercise, and that's right. And you also, it's good to do endurance, and for some, it's really nice. I would say on an individual basis, what works.
Yeah, there is a new study from 2023. My supervisors, that it's a study where they're trying longer durations, and then they're trying shorter durations, and the preferred duration during the intervals was one. We extrapolate to that to adherence, then perhaps it's short intervals that they prefer.
Yeah, precisely. And then finally we go to paper 4. Troels, time. In this study, you started up by having 169 CAD patients. And now, this, as we go down this way, it reminds me about a children's song called 10 Small Cyclists. Because then we go further down. Then we go to 142 patients complete appearing here.
I think there were two. What we had to do was that we had to get a new written consent before we could ACE genotype them, because it wasn't part of the original protocol.
Okay.
And yeah, this was probably in the midst of all the corona conspirations and everything. So a large portion said, no, you may not look at my genes. So that's that.
Quite different from if you look at the percentage. I know it's not really, but compared to the young ones, to the study one actually here. But never mind. Then you put those two together, and then you look at those doing exercise but not having ACE inhibitor treatment, and then you found these two small groups, and then you find no difference. Is that a surprise?
Those are really small groups, and it had to be an extremely determining effect of the gene if we were to detect it. So only for the adaptation. If that was the case, then I believe that we would probably have seen an effect. Probably, yeah.
Good. Okay. The grouping of ACE inhibitor treatment, as you were not stratifying, because that was not the idea at the beginning. So, but could that have an influence?
On VO2 max?
On the effect of it. It doesn't matter.
But yeah, in the original hypothesis, then perhaps.
They would have.
And we would have stratified. I don't think so. No.
We don't know.
We don't know.
And you do not know that, also now on the other ones, they are, equal. So we can say at least it's the same, but we do not marks. Now I know you're not a doctor, but the main cause we are using those are either because the patient is hypertensive or the patient have heart failure, to be very, vierkantet.
Yeah.
But to say that if it was...
Okay.
Do you see the point?
Yeah, so it could be a reflection of heart failure or...
yeah, it could be. So the one group, you didn't do echoes, and I understand why you didn't do that, but if you do not know whether they had a systolic function, you had a prior ejection fraction, I guess, from time of the echo could have been, I guess... Yeah. So...
Yeah, and if here is to see, we're looking at
the change.
So if your response is different.
Okay. So taking together, where are we going ahead? To scores, and here, when you start instead having the clinical problem like coughing that you have when to different genetic losses, and so if you knew the genome stuff.
You hear me, Troels and Torua?
We can hear you. Okay, should I just start? Yeah. Okay, thank you. So first I will thank the universities for letting me read your thesis and be here today to discuss with you. I really enjoyed reading the thesis, and I really enjoyed your presentation today. That was a very clear presentation of the results and the studies, and I also enjoyed the discussion you had with Hanne in the first part. And as I said to Hanne, it was almost like looking at you dancing, because you were moving, approaching each other, and so I think I will be more static standing here. So I'm not a good dancer as Hanne, so it will be more of the pure discussion, I guess. Okay. So, yeah. Okay, so first I will focus on the muscular adaptation. I will also focus mostly then on the results from paper 2. But I also will touch upon some parts in your introduction. And in general, I think the introductory part was quite well written. It was some differences from part to part, but in general, it was very well written. And I especially liked the discussion you had on the genotypes and the trainability, which is quite complex. There were, however, some of the terminology that, at least from my perspective, was not that clear. And I've listed 4 or 5 terms here. So, for instance, cardiorespiratory fitness, VO2 max, exercise capacity. Is it the same, or what's the differences between these terms?
Yeah, you could say VO2 max is well defined, and MET is well defined. Cardiorespiratory fitness is not well defined, but it's typically used as an analog to VO2 max or VO2 peak, and it's typical in the more clinically oriented journals where they use cardiorespiratory fitness. And yeah, I think I use exercise capacity a lot, just as the as covering over everything, but exercise capacity is more, it could be, for instance, your maximal effort during a 6 minutes time trial, as we did in the rowing performance. And the best definition is from the Michael Joyner paper in Journal of Applied Physiology. I don't remember the exact definition he uses, but it's VO2 max and the percentage of VO2 max that you can sustain for a prolonged period of time. And
yeah, so that's
so it's not the same.
Yeah. So that's the most used definition. Much problem is perhaps with exercise capacity that it's mainly relates to VO2 max, whereas you also have exercise capacity as lifting heavy loads, etc. So this close relation to VO2 max for exercise capacity in general is a little bit challenging, at least for me, as works more with resistance exercise and those types of exercise. And I think you refer to exercise capacity mainly as related to VO2 max also in your thesis.
I did, yeah.
Okay. In your introduction, you show this figure that you showed in your presentation, and I think Han also showed it. So, what I was interested in this figure was this large variation within each group.
Yeah.
So, for instance, this here in the DD genotype has a serum ACE concentration similar to those in the II. And is this because there are some measurement errors, or are these concentration measured repeated times, or is it fluctuating, or what's the reason for this huge variation within each?
Well, what Rigat and colleagues find is that the insertion deletion polymorphism determines 47% of the total phenotypic variance, and that means that there 53% is not explained by the ACE genotype. So of course there can be huge fluctuations. I'm pretty sure that this is based on one single measure, and the new, if you look at the literature now, I think there's a consensus that it's more likely that the ACE genotype explains between 20 and 40% of the variation, and not as high as Rigat found.
Okay, so this is extreme.
Yeah.
So if this is a real measurement, do you think, is it the genotype or is it the actual serum concentration that would dictate whether the trainability is affected or not?
That depends. If we believe that it is the phenotype based on the ACE genotype that determines the trainability, then we would imagine that that one responds as a carrier of the II genotype, for instance. But I don't think there's a clear mechanistic link between the serum ACE activity and your ability to respond to exercise training. So I don't know if it's the ACE genotype and there's some other gene in linkage disequilibrium with the ACE genotype that perhaps explains it, or so I think that's difficult to answer.
Yeah, and I follow that. So although you indicate that the II is more towards the endurance type and the DD towards the high muscle mass and strength, this huge variation within groups could also be one factor that actually explains why it's so difficult to find very clear differences perhaps between these genotypes as well.
Could be, yeah.
Okay. And I guess you would also say that the purpose of using the ACE inhibitor is to get this kind of phenotype.
Yeah.
You have some nice figures in your introduction as well, and you showed this in your presentation. So I like this a lot because it shows the causal relation up here, and you also show where the different factors that you can affect with training or with the medication, and how that can influence the changes in VO2 max. So actually you could have used this even more than you do in your thesis. You could have come back to this as well, and also explained with your results how it impacted the different parts. You did that partly in your presentation, and that was very good. But I had some challenges reading this in the beginning. Especially, it took some time before I saw the pluses and the minuses appear. So some different colors could have increased the readability perhaps there. And then I also spent some time to understand the minuses and the pluses here, but finally I grabbed it. But could you just explain the minuses and the pluses up here?
Yeah, so an increased red blood cell volume will increase the arterious oxygen, what's called pressure.
Yeah.
And the other adaptations that that improve our capability to extract oxygen will then result in a reduced venous oxygen.
Yeah. So at first I tried to see that all these arrows pointed at the difference itself, but it's on the arterial side and on the venous side. So yeah. Good. And I will come back to this figure when we discuss some of your results later. So, after the introduction, you end up with this hypothesis, and I will look further to those highlighted in bold here. I also highlighted some in yellow here. And I think that was because I had some more specific question to why you ended up and how you dealt with some of this hypothesis. So the first part is about the muscular efficiency. You mentioned that a couple of times during your presentation, and you were also slightly discussing that with Hanne. But when I looked at paper 1 and 2, it was hardly discussed there. And that's maybe because you didn't see any effect of the medication on that part?
Yeah, and because we saw an increase in the steady state oxygen uptake from pre to post intervention, whereas unchanged would perhaps be okay, but when we see a significant increase in steady state oxygen uptake from pre to post intervention, I don't know. We were a bit afraid that there might have been some measurement errors or something, and of course when you don't see anything in the or when you don't see anything in the data, we didn't write a big story about it.
So we can go back to the results later. But did you do as you're supposed to do, that you had this hypothesis before you did the study and saw the results, so that this were the actual starting hypothesis?
No, the starting hypothesis was related to an increase in upper body muscle endurance. So that was not one of the. We didn't have that hypothesis when we published the study on clinical trials, for instance.
Okay. That's okay, and sometimes that's needed in some circumstances. But of course, the correct way to do it is to have all these hypotheses. And I guess some of these hypotheses, I haven't checked that, but in your registered clinical trials, most of these hypotheses was mentioned, I guess?
Yes, so some of the hypotheses, but what we also tried, or I have tried to make clear also that that this was more of a exploratory study to see that we look at broad spectrum physiological adaptations, and so if we manipulate the ACE phenotype, if there's an effect on, for instance, muscle endurance or on VO2 max, then where is the effect? Where can we track it back to? The oxygen carrying capacity or local muscular adaptations, and sometimes then you just have to find a direction when you write a paper, and so.
But the design of the study was made mainly to see differences in the VO2 max, as you discussed with
and muscle endurance.
Good. I guess the reason for highlighting the part here with the left ventricular mass, if that was one of the main hypotheses and the main research questions, why did you only do 8 weeks of training?
Yeah, that's a good point. And well, there are several answers to that question, and one of them being that we give 20 milligrams of an active pharmaca to individuals that have to continue their daily lives, and we saw that there were some side effects, and there were people working up in high buildings and stuff like that they were afraid that they would pass out and stuff like that. So there's a balance between you know how long can you continue, and also how many resources do you have. So yeah, we were using training facilities and rowing ergometers, and all sessions were supervised, and it's a costly project. Of course, we would have wanted to train them for 16 weeks, perhaps.
Yeah, so I totally understand the practical challenges by conducting a longer study here, but perhaps the consequence of that would be that perhaps you would remove this hypothesis.
But I think an argue against that is still that the studies by Nils Secker and Benjamin Levine and others, they have shown that there's an extreme cardiac strain when doing high-intensity rowing ergometer training. And they have used arterial catheters where they have measured an average mean arterial pressure of 250 millimeter mercury during the rowing movement. So we thought that perhaps if there is a endurance-based training that can induce cardiac adaptations after only 8 weeks, then perhaps this would be a perfect training.
So are there any other studies using rowing exercise showing this cardiac adaptations in 8 to 10 weeks?
Yeah, I refer to two, but they use no, they haven't seen in the left ventricular mass, but they have seen dilation of the heart and increased atrial volumes and stuff like that.
Yeah.
And they have not used rowing. Sorry if that was what you asked.
Yeah.
No, they have used 8 weeks.
Yeah.
and not rowing. But
Yeah.
I haven't seen rowing studies in sedentary individuals or previously sedentary individuals. There are very few studies.
Okay. So you also have this hypothesis here that the ACE inhibitor would have a better effect on muscular efficiency and also on local muscular endurance. So after reading that, I was a bit surprised about how you had this title of the second paper here. Can you see what I'm referring to?
Yeah. Despite ACE
Yeah.
inhibition.
Yeah. So why despite? Didn't you exactly expect that ACE inhibitor should improve this adaptation?
Yeah. Why did we end up with that exact title? That's a good question. I think the more comprehensively I dig into the literature, those studies that resembled ours that were done in animal studies, there are very few studies in human, and they have found a mitigating effect on citrate synthase and HAD, and so I think that was why we wrote the title as that.
Yep. Okay, that's also understandable. But I'm glad that you also see the conflict here.
Yeah.
So we mentioned muscular efficiency already, and I think this figure is only shown in your thesis and not in the paper. Is that correct?
That's correct.
Yeah. So so the reason was that you actually saw an increased oxygen consumption at both these submaximal intensities in both groups here. Is that correct?
It's correct that we saw that, and well, I think it's difficult to explain.
Yeah.
Perhaps a bigger increased beta oxidation, which has a higher energy cost per oxygen, not per
Yes, you need
molecule.
more oxygen per energy unit.
Yeah, but I don't think that can explain I don't know, what is it, 150 milliliter increase in the
So, but what you had expected was actually a decrease here in the ACE inhibitor group?
At least if they were training on a cycling ergometer, but when they're doing when we're testing on cycling ergometer, training them on a rowing ergometer, then perhaps unchanged or slightly improved maybe.
Yeah, that's interesting. So just for this this variable, it might have been some more challenges by shifting from one exercise to another test.
I believe so.
Yeah. Good. You said that increased fat oxidation might explain this. How could you measure that?
Well, we can look at the we get the RE what's it called, RER.
Yeah.
And I haven't looked at it to see if it's different from pre to post to see if it's a larger fat oxidation.
But you have those data.
I have those data. I haven't looked at it.
Yeah, so that should be easy to check. What else could affect the oxygen uptake you measure here?
Well, I don't know, motivational factors.
I'm not sure because they are cycling at the same absolute.
Yeah, I just think
load,
that.
so,
Well, I could. It's just that I could feel on the participants that they really wanted to perform, but yeah, it's a submaximal test, and I agree that it's maybe not that will increase their.
But have you subtracted the resting metabolic rate here?
No.
No. Could that affect?
Yeah, probably. If they were, you're thinking they got a higher body mass.
At least
lean mass.
At least in the placebo group, the lean body mass increased. So
so an increased lean body mass, could be a factor.
So,
but
you didn't measure the resting metabolic rate, I guess.
No, and it wouldn't really explain the increase in the ACE inhibitor group.
No, if it hadn't increased the resting metabolic rate for other reasons, of course. So I guess at least when you have this very low intensity exercise, you should actually measure the
resting metabolic
perhaps
rate.
the sitting metabolic rate on the bike before you start, and then you can have more sensitive measure of the efficiency during exercise.
Yeah.
Okay. So I will also discuss more in detail these methods. You had a lot of discussion with Hanna on the cardiovascular responses, and especially the cardiac responses. And you have already had some discussion on why you measured the VO2 max on the bike, but we can come back to that. Muscle endurance, if I understand correctly, it was measured in something that looks like this.
Yeah.
Is that correct?
Yeah, but we call it custom made because we made some modifications to the machine.
Yeah.
So they were more in a fixed position.
Yeah.
And,
but it's like this, and to this position?
Yeah.
Okay.
90 degrees.
Yeah. So, which muscles were mainly doing the job here?
Well, we had an active in biceps and the posterior deltoid and what's it called? Latissimus.
Yeah, I guess latissimus must be very important.
Yeah.
So, did you ask the participant, or have you tried it yourself? So,
yeah. Multiple times.
Yeah. So, where did you get the most fatigue or felt the most soreness?
Well, I felt in the latissimus and in the biceps primarily.
Biceps. Okay. Yeah. Good. Unless you had the hand grip strength, and what was the main rationale for choosing this as a strength test?
Well, simply because it's convenient and extremely easy to do when we're doing all those other exercise tests. Then it was easy to put that one in, and we at the time we didn't really have anything else here.
Yeah,
so
that's make a difference. Yeah. Because if you had the possibility to test perhaps more of the larger muscle groups used in your exercise, would you have chosen that, or would you still?
I think we would have chosen that. Yeah.
I agree on that. And then you had body composition by DEXA in the first study?
In study 1, yeah.
But not in study 2?
No, in study 2 we used bioimpedance. Yeah, and it's because there's one DEXA scanner here in Tórshavn, and getting 142 patients was impossible.
Yeah.
So,
but it could be possible to do a subgroup to have a good measurement in a subgroup into both groups, perhaps. Or?
Perhaps.
Yeah. Because you also write that with bio impedance, you had some challenges as well, so you didn't get too many.
It was after several patients had been through it, there were some. We found out that there were some wrong measurements, and we sent it to Denmark, and they analyze it, or where they have the base.
Okay.
And all of the measurements that we had done up to that time could not be used. So we got a new one, and we then used that one. So only half of the participants.
Okay, so that's the reason.
Yeah.
Okay. Yeah, and then you also had the muscle biopsies, of course, so that you could look at the muscular adaptations. And you said that was some of the reason why some did not want to participate, and that is understandable. But it was quite an impressive number with muscle biopsies.
And everyone was okay with it. Yeah. It was just that some challenges in the deltoid did that we had a lower sample size.
But you didn't give too many details about the biopsy procedure. So how was which technique?
Well, the Bergström.
With the suction.
With the suction.
So how much tissue did you normally get from each biopsy?
I don't know the exact amount of tissue.
I will come back to some issues related to that. So. Okay, but before we start to discuss some of these results from these methods, we could have some more discussion on the exercise protocol, even though we have already discussed quite some aspects of the exercise protocols. And I was very impressed by the training adherence, both in study 1 and study 2. So there's something with you people here in the Faroe Islands. I think that's, it's...
When you sign up, you complete it.
You complete, that's... I think that's good. Hanna also asked you this question about the training intensity, and I guess what Hanna was referring to was why didn't you look more to the heart rate? Why only to the power output during the exercise?
A lot of the answer will be that we simply didn't have the equipment.
Okay.
We didn't have equipment. We didn't have pulse belts or measurements.
Okay.
And what else could we use? We could have used percentage of VO2 max, but VO2 max was completed on a cycling ergometer, so we can't translate that intensity to the rowing ergometer. What else could we have done? We could have said, well, some say that if you go all out on a rowing ergometer, 2-3 minutes, then the final 30 seconds will be representative of the intensity of your VO2 max. So perhaps we could have done something else, but we did a 6-minute all-out test that we used.
And that's the percentage that is given in this column. So what would be the advantages by also including heart rate as for just looking at the quality and the effect of the training?
To see so that we have more measures at which intensity they're working at, and of course we want them to when we're doing high intensity interval training, we want them to work at a high percentage of their heart rate.
And why is that?
And because this it's high effort is associated with some physiological adaptations.
Yeah, and if you try to explain more what's happening to the heart during this high intensity exercise, and that might be the stimuli for exercise or training effect.
So there's an increased sympathicus outflow, which increases the contractility of the heart and the strain on the heart, and we have high metabolic disturbances,
So in summary, you would probably get more information to see if all the individuals had the same stimuli on the heart, and then also whether it should have influenced the training response. But I guess the approach you take here by having this 6-minute all out and a percentage of that gives some of the same answers probably. But the challenge here might be that you might have a large individual variation in the effort in this 6 minutes all out as well.
Yeah,
if you have some additional variation there, that will be more errors in these measurements.
But I also think, but if we use, for instance, the intensity corresponding to 70% of the participants VO2 max, then that will be easy for some and maximal effort for some.
Yeah.
So it's not like percentage of heart rate or percentage of VO2 max. Well, it's difficult to standardize the homeostatic stress on an individual level by looking at that.
Yeah, that's true. Okay, you choose quite short intervals. In study 1, I think it's less than 4 minutes. It's not explained exactly what the duration was, but
4 minutes or less.
4 minutes, which means?
Which means
2 minutes?
We used, it was not the same intervals all the time. So some of the intervals were 4 minutes, 4 minutes break, repeated 4 times. And perhaps on a Friday it was 10 times 1 minute. And I think there's I think the training program is attached in the supplementary. I'm not sure. And what we did here was that we asked, we had this, we said that the training intervention is to be high intensity interval training, and then we talked to some rowing experts and asked them to translate that into how would a typical 8-week training intervention look like for elite rowers. And that's what they did actually. Largely.
So,
and then of course we wanted to have power output and other things so that we could monitor. And
even though we can agree that the heart rate during these intervals doesn't say exactly what the training stimuli are, but what's the typical changes in the heart rate if you have a rather short interval versus a 4-minute interval?
There's a high fluctuation, I think, and you may not reach your maximal heart rate in a short time.
Yeah, at least you have a shorter time with a very high heart rate with a very short intervals. And in theory, that could have influenced the training effect on the heart as well, of course. Yeah. So if the changes in the left ventricular volume or anything was the main goal, perhaps that should be the focus then on how you design the training as well. But you had several main factors that you wanted to have an effect on. So okay, and in the patient, the training duration was a little bit lower, and also the relative power output was a little bit lower, but not a lot.
In study 2?
Yeah,
Or what are you talking
yeah, in
about?
study 2, yeah. That's what I've highlighted here. So down to 12 minutes of active interval training or 18 minutes per session.
Yeah.
So,
Yeah, yeah, the active training time was a little bit lower, and that was one of the difficulties with as Hanne also said, with this patient population is that they don't adhere to the training, and we try to get the active training time, or the training duration as low as possible and the intensity as high as possible, and see if we could get the same effects with only 18 minutes per session. And what I didn't mention in the picture before is that there's a large portion of these cardiac patients that have continued their training under Tony Dam supervision because they really like this training form.
Yeah. And they saw the benefits of it.
They saw the benefits, yeah.
Good. Okay, so also some more details on the methods before we go to the results. And you mentioned that one reason for choosing the cycle test instead of another, you could probably have measured VO2 max in rowing as well, or?
Probably. It requires a whole body movement, and it would probably work. Yeah, maybe. We haven't tried to measure VO2 max, but I believe that we would have to change our setup at least with the online system and everything. But
because of the movement.
Because of the whole body movement, and
it's possible to get some slides under here actually, so
I've seen
the
those
participant is stable and
I've seen
equipment
those
is
in
moving.
Team Denmark. Yeah, I've seen them.
And then you argued that you would remove the learning effect, if I remember correctly.
Yeah, or the familiarization.
Familiarization effect. Yeah, that might be a point, but one of your main variables is to look at peripheral adaptations, muscular adaptations. So what happens when you move from this exercise and do this test?
Well, we only use the legs in cycling, whereas we use whole body in rowing.
Yeah. And you have measures from vastus lateralis, which is involved in both, of course, and is probably a very important part. But if there are other changes in the latissimus, for instance, that's a main muscle here in the upper body, you might have got different results if you had looked further into a test involving that muscle, and also perhaps had biopsies from that muscle, of course. So, so you lose some of this more peripheral adaptation, which is, of course, directly specific to the exercises you do.
Yeah, that's a good point.
And I think that's more, you have more control of that in this endurance test, I guess. But what I was asking here is the load that you use is for 40% of 1 RM elbow flexion, which is this kind of motion?
No, so we put 100 kilos of weight on that, as you can see there. And then we fixed it. And then we put a power dynamometer, so they had to pull just as they do the same movement, everything that they could.
Okay, so it was still the pulling.
Yeah.
Okay.
And then we took elbow flexion. I don't know.
Yeah. So I wouldn't have written like this.
That sounds perhaps like a biceps curl or something like that.
Yeah. Okay, but then I understand. So it was 40% of the isometric max.
Yeah.
Good.
Exactly.
Okay. Thank you. Well, we have discussed some of these issues, and you didn't have so many different tests to choose from here, so that's okay. What's of interest when it comes to the biopsies and some of the other tests is, of course, the most important muscle you use in rowing, and you don't discuss too much about that especially in the papers. You say some more in the thesis, but what would you say about the most important muscles and the muscle that you expect the largest training adaptations after this exercise?
It's clear that when you we also did a pilot study actually where we measured with EMG electrodes, and it's clear also, as you can see, that it's the biceps that do the primary mover, and you also use your lower back, and the pulling movement we saw when doing the pilot study. We saw activity in the biceps, activity in the latissimus, and in the posterior deltoid.
So it was a large activity in the posterior deltoids as well?
We saw a larger in the biceps, but perhaps Erik Richter could have taken biopsies, but we were afraid of the brachial artery, and Magne has experience in taking biopsies from the deltoid from previously. So I agree there could be a muscle that's more representative of the movement, but
so I'm not sure. The biceps could perhaps be some individual variation also, because you can use your lats the most, or you can use the biceps more. So that's also probably challenging, but it's no big problems to take biopsies from the biceps actually. So that's
I can't do it, but someone can.
It's quite clear why you used the vastus lateralis, I guess, because that's main muscle in both the test and the exercise, and also an easy accessible muscle. But you had some biopsies, or most biopsies, and I think that's logical, from the posterior part, but it's written also that you had some from the anterior?
That was simply when there was too much fat tissue that we couldn't take in the posterior part, and the activation in the anterior part is probably non-existent.
So
we also did analysis without those.
So did you compare? Were there differences in?
I didn't see differences between the anterior part. I don't know if that's some crosstalk or something. I don't know.
But it was also very few with the anteriors.
3% or what it was.
Then you had quite a nice, what should I say? A lot of targets in the muscle biopsies, and you measured from the glycolysis all the systems in the mitochondria. So I think it's quite logical why you chose all those, and also the electron transport chain. And then you had this PCAM1 as well as the main indicator of vascular changes, or what should you say?
Well, the simple answer to that question is because they had the antibody on the laboratory, and they have experience showing that it is a marker of initial angiogenesis. Should we have included vascular endothelial growth factor 1? Yes, probably. We know that the muscle contains VEGF1, and we know that it's released during contraction, and we know that it stimulates angiogenesis.
But that's probably even a more acute rapid marker, I guess, because it changes after each...
probably we would then have to take the acutely out.
So if I jump to this, what do you see here?
Well, that's a cross-section of a muscle stained. And I think there's muscle fibers and there are capillaries.
Yeah, so the red dots here are capillaries. And do you know which antibody we normally use to mark these capillaries?
Nope.
No, it's the same as you use mainly. We call it CD31 here. But the reason for bringing this up is you have some more information from analysis like this at least for the capillarization.
Yeah.
So what would be the main differences or the main information you get from this that you don't get by only measure the total amount of PCAM1?
Well, PCAM is only a marker, potential marker of angiogenesis. And here we can count the capillary to fiber ratio, and we can calculate the capillary density.
Yeah. And you can also relate it to type 1 and type 2 fibers.
So that's a more functional measure.
But when you do take these biopsies, why don't you also prepare some samples for immunohistochemistry?
Yeah, I don't know. Perhaps we didn't have enough tissue, or yeah. If we had the possibility, we should have done that. But we did protein-based analysis. So. But yeah, it would definitely give some more information.
Yeah. So the analysis you did on PCAM1 was Western blots. Normally, when you do Western blots, you present the quality of your blots, like showing the blots like done in this paper. This is one of the references you have. And if you look at the band here for PCAM, it's not a very good quality. The band, did you do this measurements yourself? Or?
No, they did it on the I was stationed here during the COVID pandemic, and they did it on the.
But have you seen how the bands actually looked in the?
No, I haven't seen it.
Okay.
No.
And this is published, but the journal didn't ask for these results either.
No, they didn't.
That's strange. Yeah, because you can have very good quality Western blots and you can have very bad quality Western blots. Okay. And if you have good quality, you can of course trust the results. If you have bad quality, the results tell you nothing. So from what I saw in your thesis, I can judge this part of the. Okay, but that was for the methods. So the more exciting part is, of course, the results. So the last 10 minutes or so, we will focus on the results. And what still gives me some challenges is that you have the same in study 1, you have the same increase in VO2 max in the ACE inhibitor group as in the placebo, but you have significant differences in the plasma volume, especially in the red blood cell volume, or perhaps more especially in the hemoglobin mass. And that should actually give a difference in the VO2 max in favor of the placebo. You discussed that perhaps here on the peripheral adaptation, you might have the better results. That might explain why the net result is similar, but you get exactly the same results on the peripheral adaptations in both groups, and you have a huge difference, or at least a significant difference in the more central adaptations. So
I think it's
could it still explain that you should get the same result for the VO2 max?
No, and well, the interpretation of this has also given me a headache. But what's also important to mention is that there's a significant between group effect, but the placebo group doesn't actually increase their oxygen carrying capacity of the blood. It's unchanged, but a numeric slight decrease. Yeah, and of course the significant reduction in the oxygen carrying capacity in the ACE inhibitor group. Yeah, you have lower your capacity to deliver oxygen to the working muscles should be decreased, but why we see a similar effect in the VO2 max, I can't explain that based on the data that we have.
I also find it hard to explain that directly, and especially since I guess this question marks here also indicates that it's open for discussion how important or how much effect you can have on these adaptations. So,
yeah, you usually say that it's the central oxygen delivery factors that are limiting for VO2 max.
So just based on that, we would have expected that VO2 max was increased more in the placebo group than in the ACE inhibitor group here. Do you think you had measured something different if you actually had measured VO2 max in the rowing exercise instead of the cycling exercise?
Well, I can't say that there will be a difference between groups, but perhaps I would expect that we would have seen a higher increase in VO2 max.
I agree on that. But it would be interesting to see if perhaps these changes in blood volume, hemoglobin mass could have a larger effect there as well. Due to the time, I think I skipped this one. The reason just for having it in here was to discuss why they find these large differences and you don't see it. But I can have one comment. Based on this response with ID and the DD responding similar here in the left ventricular mass, why did you group the ID with the II in the second study?
Well, I did both analysis.
Okay,
I did II, ID, and DD, but it's because in the literature they really often just say that carriers of the I allele and carriers of the they compare carriers of the ILL to carriers of the DD genotype. That's what you see consistently in the literature. And in this figure, it looks like the DLL is an incredibly defining gene. So that wouldn't make sense to
I understand. This finding in muscle mass was perhaps the one that was more at the expected side. You also started to discuss with Hanne some of the mechanisms for why the ACE inhibitor maybe reduced the changes in muscle mass. Could you elaborate on that?
Yeah, it's pretty much based on the studies by Owens, who's shown that angiotensin is an important growth factor for hypertrophy in myocytes, and then studies have done animal studies have tried to do these overload-induced protocols with rodents where they infuse where they give ACE inhibitors and they see that the hypertrophic response disappears, and then they infuse angiotensin 2 and they see that the response comes back to normal. And I don't think the mechanism is well described, but if there is anything there, I think it would be that the angiotensin 2 could function as a growth factor.
So has it been shown in these studies whether it goes through the mTOR pathway or where it goes?
No, I haven't seen that exactly, no.
Okay, but at least this is an interesting finding to follow up on. And you also have the reduction in fat mass that is similar in both groups. I guess that's simply because of the exercise and perhaps also the effect of being in an intervention study. So we don't have to go into that. The muscle endurance that's improved similar in both groups. And again, here the hypothesis was perhaps that the inhibition group should have a larger improvement.
Yeah, if we base it on the upper body muscle endurance in the Montgomery studies, then we would expect an additive effect of ACE inhibitor treatment.
So this study.
Yeah.
And when you look at the factors that should explain that, that's of course related to the both the possible capillarization, mitochondrial adaptations, etc. And in a way, this supports your finding that it's no big differences because it's mainly the same changes. You find some exercise-induced changes in both groups in most of these variables. And you present them in tables like this, so I won't go into the details here, but just to remind you that for all this, I would have liked to look at the quality of the measurements. And then I think for the deltoideus, I think you perhaps was this the one you showed in a figure that you didn't have in the thesis, because you showed one figure that actually showed a difference between groups.
That was citrate synthase.
It was citrate synthase?
Maximal activity.
Okay, yeah, so, sorry.
Citrate synthase maximal activity in the deltoid, where we saw a significant, we saw an increase in both groups, but a higher increase in the placebo group.
Yeah.
But again, in the deltoid, the sample size is, what is it? You can see, if you go one slide back, that's the Western blot.
Yeah. So I just thought you had the same. This is the same indication, isn't it, as for the citrate synthase, that you have a higher increase in the placebo group. No, sorry, it's the opposite. It's the opposite, isn't it? For the maximal activity for citrate synthase, you showed.
Yeah, if you go back, you had the figure there. B, you can see a Timex treatment. We have an interaction effect, significant interaction effect.
So that's the one we showed.
So the two groups change significantly different over time.
Yeah, with more in the placebo.
With a 57% increase in placebo and 27 or something in the. But again,
so the same direction actually as for the complex here.
The complex 4,
yeah.
But those had so incredibly high variations.
But opposite from your hypothesis again.
The hypothesis would be that.
And also, if you look at this complex here in the deltoid, it goes this direction in the vastus lateralis. Although it's significant, it goes the opposite direction again. So, with a larger increase in the ACE inhibitor group. So, there's a lot of variation here. So, I guess it's not. We can't trust too much on some individual data from these results. Okay, but from all the results you have gained now, and when you have reflected on them, what's the main message from your PhD study that we should bring with us when we leave the room now?
Well, I think one important thing is also when I have been writing my thesis is that the fallacy that looking at one gene and thinking that we know enough about genetics to say that if you got this genetic variant, then you'll be an endurance athlete, and if you got this genetic variant, then you'll be in strength and power athlete. I think that is fundamentally wrong.
Yeah, I totally agree. So I think that's a very good take-home message. So besides that, life is going on, of course. So I think Magni told me that you are doing some teaching now. But what are your plans? Are you going to follow up on these studies, or what are your plans in life?
Yeah, we have an application for doing another study where well, the plan is to continue also within these, but also to look more at the interaction between other medical treatments and exercise training, and to collaborate with Fargene and well, use bioinformatics and stuff. But we have an application where we will look at statins, and together with University of Copenhagen and others.
So doing the intervention here on
that's the plan, because we there was recently a PhD defense showing that the prevalence of familiar hypercholesterolemia here in the Faroe Islands is much higher than other places in the world. So it's a homogeneous population, and it's interesting to do genetic research here.
It will be very interesting to follow that study as well. So I hope you get the possibility to do that. Okay, I will end my discussion there. So thank you. I really enjoyed the discussion.
Thank you.
And then I think it's open for some possible questions ex auditorio. Is that correct? Yeah. So if anyone have some questions to Torur, I think this is the time to bring them on.
Actually, I have a question. Can you hear me?
Yeah. Good, Lars.
Hello?
Yeah, we can hear you.
Hi, Lars.
While we are waiting, if somebody in the audience has a question, I also have a question. Now, first of all, I want to thank Hanne and Truls. You have done all the hard work. That's the nice thing about being chairman. You can just lean back and you will do all the work, and you have done excellent going around. You had a little of a question here at the end, because we should not forget that a PhD is actually a doctor of philosophy. And although we work in health science and in natural sciences, I would like to ask a little of a philosophical question. Your findings are negative, so to say, in the sense there's no difference of the interventions, there's no large differences in the genetics. So are there any positive things in having negative findings?
Not when you want to publish in Nature.
No, I agree on that, and that could also be the explanation why studies with such a large amount of different measures are ending in European Journal of Physiology and so on. But do you see any positive things in this?
Yeah, of course. I think there are positives, and I think it's incredibly positive or important that we publish our negative findings, and that when you're doing a high quality randomized control trials, that you can publish in higher impact journals, even though...
but that's from a science point of view.
Yeah.
What about the societal? I mean, we always look, the scientific impact. What is the societal impact of this?
Well, the societal impact is there are several factors. You can use your ACE inhibitor and still gain important physiological adaptations.
Exactly.
And
I mean, it's very positive that Hanne can go back and say, okay, if I give some of my patients in Alprine, they can still actually benefit from training.
And another
Or
important...
if you have your heart patients, you don't need to test them for these genes. You can still say, well, do you exercise, because you will probably benefit from it.
Yeah, and with regards to the ACE genotype, then at least you can't use that as your excuse that you got the wrong ACE genotype.
No, exactly.
Yeah.
Good. Now I will ask Truls if you can be my eyes. Are there anybody in the audience having questions?
Not as far as I can see. If anyone has a question, please raise their arm or ask the question. No.
Otherwise, you have done HIIT training, and this has been more of an endurance session. So I think we will end it here, and then Truls, Hanne, and I will have a brief meeting before we will call you back in.
Yeah.
Truls and Hanne, maybe you can go to the same microphone, or and then if we could have change for the camera angle. Hey. til, sådan, så jeg også kan se Torur-rummet eventuelt. Bare sådan, så at man både kan se speakeret og mig.
Vi kan se dig.
Vi kan se dig, Lars.
Ja, men her igen. Jeg kan ikke se jer.
Ja.
Det er lidt tamt, kan man sige. Kan du høre, om han kan dele? Sådan. Nu kom Kongshøll op igen. Hello again.
Hi.
It is unfortunately so that the committee here cannot award a PhD degree, but we can recommend to the dean that he will award it, and we agree that that is what we will do. So we will recommend both the Faculty of Science, the dean there, and the dean at the, how's it pronounced? Fróðskaparsetri Føroya, the Faroe Island, to award you. So you will have a double degree if all goes well, as they have informed you. So congratulations, Toro. It was a pleasure to see you present and also to see you discuss, and at least also a little philosophy on your work.
Thank you.
And now I hope that you will also have the time to celebrate both with your beautiful family as well as the visitors from Copenhagen and so on. I'm going to do a study in the next days, and I also had teaching today, so unfortunately I will not join you on that, but nevertheless I wish everybody a pleasant evening, and congratulations to you and your supervisors.
Thank you very much. Tusind tak for det. Yeah. Let's eat and celebrate. I've been talking enough. Tak. Ja, tak.
So enjoy it. Bye bye.
Ja, tak.